Good morning, and thank you for joining us today. Welcome to this latest installment of the EuPRAXIA virtual seminar series. Today we have Dr. Paul Crump, who is head of the Photonics lab at FBH Berlin. His seminar will focus on diode lasers for the next generation of ultra-high energy laser applications, from direct material processing to inertial fusion energy. Just before we start, if you'd like to ask a question, and we do encourage you to do so, please use the Q&A function within the chat, and we can put these to Paul at the end of the presentation. Thank you once again for joining, and I hope you enjoy the seminar. And if you're ready, Paul, over to you.
Thank you very much for your time. And again, apologies for the short delay at the start here. I very much appreciate your patience. So I'm going to be talking about diode lasers for very high energy laser applications. Laser plasma acceleration is one very prominent and very important one in that. And so hence this is part of the EuPRAXIA seminar series. Very great pleasure to be here. So I'm going to run through a few examples. So there's going to be start up with an introduction and what is worked on in terms of the topic of high-powered lasers at the Ferdinand-Braun-Institut in Berlin. Run through a detailed worked example. So some studies on our side in experimental physics into the limits to optical power. A brief overview on limits to conversion efficiency in diode lasers. A brief overview on limits to the beam properties. Supporting ultra-scale applications. For example, this very exciting emerging field of inertial fusion energy and what role do diode lasers play in that. And then conclusions and next steps. So straight into the overview. I mean, the Ferdinand-Braun-Institut is a national/international excellence center on 3-5 semiconductors for electronics, photonics, quantum technologies. There are devices for health, nutrition, climate, energy, mobility, security, the wide range of exciting applications. There's a large 2,000 square meter clean room in the institute where we make all kinds of devices from bare epi through to application-ready modules. Lots of transfer, about 400 people. So it's a reasonable sized institute, and we can do lots of things to help the high energy laser community, amongst other important users of laser technology. So high-powered diode lasers is part of that scheme, part of that portfolio. It's a key enabler for future industrial and other applications and research applications. Gallium arsenide-based broad area lasers are the world's most efficient light source, the best way to convert electrical input energy into optical output energy. And they're an essential source of optical power for a huge range of emerging applications: medicine, material processing, additive manufacturing, defense, high energy laser research, of course, within the EuPRAXIA community, up to the largest application of all, of course, being fusion. So how do we get there? I mean, there's decades of design and technology development in-house for power scaling, innovative design based on leading edge innovative simulation tools, realized with advanced process tools themselves, very well equipped facility, and then assembled and tested inside sophisticated laser modules. So from concept all the way through to ready to use in your hands systems. And this is achieved in close cooperation between the photonics and technology departments. So constant performance improvement are demonstrated across a wide range of topics and styles. For example, the world's most powerful and efficient single emitters at 915 nanometers, with getting a 70-watt continuous wave output power from a rather small package about the size of the tip of your small finger, with 60% efficiency from a 1mm aperture. This highest power was for a little while the highest power out of a single laser. Also the world's most powerful and efficient laser bars, which are a key part of the systems to pump, for example, a EuPRAXIA laser, with as much as that 1.9 kilowatts out of a single 1 centimeter strip of semiconductor demonstrated, which is an assembly of devices, with much achieved in close cooperation with industry. In these two cases with Jenoptik, our partners just down the street from us, also Crump, the part of Crump is also just down the street from us in Berlin. So how does this approach? I mean, this is a simplified thing. Many people here do exactly the same development cycle, but you understand what the requirements are. You make new devices, you test them, work out what limits them, work on improvements in the device technology, the design, and then make new versions and transfer them to the customer. One recent example here, excuse me, a bit too quick. And we've been doing some work on laser-based additive manufacturing for lightweight construction. If you're building the next generation of trains, for example, like here's an ECE out of Germany, you'd like to have very low weight but very strong train walls. you'd like to use lightweight aluminium, and you'd like to have sophisticated structures that use less material to achieve the same weight. And you'd like to do that as quickly and efficiently as possible. So what we did there was a small project making 780 nanometer lasers that are absorbed between 2 to 4 times more strongly in aluminium than the conventional lasing wavelengths. And you make them into nice compact lasers so you can use them to do some fabrication. So here's one of our laser modules. This is the optical design. This is a diode laser block with a series of devices inside it, all radiating vertically. And you combine them together and dump about 1,000 watts into a small spot. And that was, we're able to show, there we go. So here's a small video of how these devices are put together. That's like your semiconductor down the middle. That's your lasing stripe with some carrying material of semiconductor. You put it together between a couple of heat sinks, solder them all together into a stack, bring a couple of water coolers onto the side, bring again in all of the mechanical supports, so it's robust in the application. You can shake it and rattle it, and it does well. Bring in the electrical connections, so you can pass some very high currents through the device. Bolt it together for strength, of course, sufficient mechanical strength. You bring in some. You want to monitor the temperature, for example, within the device. You have a temperature sensors there with the appropriate wires. You collimate the device. You bring a series of lenses so the beam can radiate vertically. And this is one of the units that then, for example, would go into this this additive manufacturing block. So each one of these at 780 gives us about 500-600 watts in a continuous wave beam, in continuous wave mode, with a beam quality out of the end that's roughly symmetric and compatible with a 1 millimeter core fiber. With enough of a gap between the beams, you can bring interleave two sets. Oops, excuse me, the next page. So this is integrated into a system. This is one of these heads in a factory in our partner's Photon laser manufacturing in Spandau, just on the edge of Berlin. And here's an example of rather noisy material processing. I mean, you get the idea. So it's device physicists making more photons out of the semiconductor and bringing them together into a useful format, putting it into a factory. And then you can hear, this is an example of using one of these things to assemble a stack of steel on a prototype plate. So we've been able to move through the course of the project from one of these heads at the start a conversion efficiency of about 35. We're up to about 50% conversion directly at the fiber, directly at the output. Very small spot. We can use different wavelengths. And then we had a nice presentation about this earlier in the year at Photonics West. Just one example, all the way through from concept. Everything's done in-house. Everything's designed, fabricated, assembled in-house from the blank semiconductor wafers and bits of aluminium for the assembly, all the way through to a module you can use in a factory. Another example is building modules, for example, compact low-weight fiber laser pumps. One important topic is narrow line spectrally stabilized lasers. And you can put them into a similar kind of stack on the previous pages, put it into a compact module with a sort of a patented approach that should be published fairly soon. You can get quite high efficiencies in a very narrow line with a good power and a narrow core fiber by leveraging the same technology platform for a different use. Also a nice exciting thing. There should be more papers on that later this year. Another very critical one, of course, for the EuPRAXIA community is using them as an enabler for emerging applications in extreme photonics. So this is a slide that comes out of an invited talk I did with Leo Gizzi from CNR in Italy a couple of years ago, also at Photonics West. Just the emphasis for the extreme photonics field. I mean, you're making high energy pulse coherent light sources up to the exawatt in picosecond to femtoseconds, and you can enable this incredibly wide range of applications with citations at the bottom here. For example, of course, high energy laser physics particle acceleration within the EuPRAXIA facility and other places like the EPAC Center, amongst others. So how is this used? Again, many of the people who are attending here will know this very well. You have diode laser pumps, a large number of them. You pump your turbo-mag amplifier. Then there's a frequency conversion to the green that is then used to pump titanium sapphire, goes into a plasma cell, and then you have the plasma acceleration effects can be made use of. With courtesy of our colleagues at STFC, this is what one of these schemes looks like within this dashed line. It's a large, sophisticated system. I mean, with this is, for example, the career cooler. This is roughly the height of a person. This is a very large, very sophisticated system developed over many years. But if you look here, there are these purple-colored diode laser pump units, and they're one of the critical parts because they are the source of the photons in the system. So all the photons that end up being used in the plasma cell come at source out of the diode lasers. And if you want to increase your repetition rate, you want to increase the brightness of your system, you want to make it compacter, more effective, it is of great help to have high performance diodes. So on a much larger scale than an additive manufacturing unit, you'd like to be working. We are working hard, and it was part of the community to deliver better technology to get a better pump for things like this. This on this screen, for example, the dipole system. One project we have running right now is funded in part by PACRI and also the EU project HotStack, EU-funded project HotStack. We're taking our experience in very efficient semiconductors and building stacks, doing some redesign work, developing our test capability, and the idea is that we make multi-kilowatt, extremely high duty cycle stacks that maybe could be part of future systems. And we're working hard within the PACRI project with our colleagues there, amongst our many partners, to make that reality. So again, watch that space. We'll be reporting more within the project and in the literature in the following months. For example, this nice paper, just to note it again, if you're interested in some more details, we had an overview there in 2024. It's on our website and also available via that link. Okay, fourth example, diode lasers for power generation via inertial fusion energy. It could potentially enable a limitless, safe, and clean source of energy. It is highly promising for that, but you need much better diode lasers in order to get there. If you're going to do it via lasers, you could say that a big part of the core of the system has been shown in the laboratory at Livermore that it can function, but you need something like a 20-fold reduction in diode laser pump cost to make it realistically to make it an economic solution. We had a series of summaries about this. Is also I'll go into a bit more detail in some later slides. I had an invited talk earlier in the year on the diode laser performance scaling you'd need for one of these systems, with a few more details. Also, if any of you are attending, there's the Compound Semiconductor Week in Japan in about a month's time. I'll be giving an update there on our latest research progress. Further example, you would like to not just make better modules and higher performance quasi-standard lasers. You'd also want to explore alternative sources. This is a very exciting kind of device that's emerging from research, low TRL, at least on our side, moving towards application. Groups in the leading group in the world, the NODA group in Japan, has shown that you can get continuous wave powers out of one of these devices of about 50 watts, which is basically, I jumped ahead a little bit. You have an array of a photonic crystal arrays put inside the semiconductor that gives you an in-plane laser resonator, but it's cleverly designed to send the beam out of the substrate. So you have a collimated beam effectively coming straight out your semiconductor with high power, with no needs to have expensive facet treatments to make the facets reliable, because there are no facets. So exciting, promising, but for very high power application, the challenge is there that the efficiency is relatively low, and you need new approaches. So we're working hard on an alternative approach in our facility that promises to get to high efficiency, but has a lot more to do. So we've been doing some new upcoming demonstrator works. We've had the first lab demonstrations of up into maybe the watt class. You can convince yourself, with data at CLIO USA and at the International Semiconductor Laser Conference in the next couple of months, based on a bunch of nice technology and design and simulation progress. Also, there'll be results reported at some upcoming special issue of the JSTQE. Okay, so that was the introduction. Quite a bit of information already. I will move on to just a couple of quick examples for the people who are in the audience who are a bit closer to the semiconductor research. So this is an overview of a gallium arsenide-based diode laser, an edge emitter. You have a current flows through the structure. You have a p-n junction where you collect current, where you collect electrons and holes so they can recombine. You can pump this region basically, and there's a vertical waveguide that holds a light in the same region. By having a very carefully designed version of this, you can get into the around 70% conversion efficiency at the operating point, and a peak of about 20 to 25 watts out of a typical 100 micron stripe. in the wavelength range of 900 to 1,000 nanometers. This is having a series of these devices integrated into a laser bar. Here you've got, it's like eight very large emitters, all emit in one direction, overscaled relative to euro cent coin. If you want to have lower cost, which is of not insignificant importance to the EuPRAXIA, the pattern acceleration community, because you use very many devices, you want to have, typically this is coupled together with increasing power. So this is a span of the last 20, 30 years or so. If you look at how the cost per euros per watt from a high-power semiconductor device in continuous wave application, how that scaled with time, it's basically followed the same trend as power per bar. So tightly coupled, you could think semiconductor is like carpet. It costs so many euros per square meter. It's simplification, but roughly. So if you can squeeze more power out of the same piece of semiconductor, the same package, then the cost automatically go down, parallel to learning lessons on automation and advanced process control as well. So if you want to get more power, one way you can do this is looking at single emitters, how they've developed in the last few years. If you look at the peak power of 100 micron stripe, we've run into some quite tough challenges to push that up. And that's been flattered at around 20 to 25 watts for maybe nearly as much as 20 years. And in recent years, there's been a strong push to make wider and wider apertures. You've gone from 100 to 1,000 micron wide devices. And this has been able to push the power up by a factor of 3, 4-ish, which is a result I showed on a couple of slides earlier. So that's one way of doing it. This is a great enabler for doing these direct diode modules. So wide stripes means you can get more power in a more compact module. The other thing you can do it in bars is you have, instead of lots of small emitters, you have more wide emitters. And that means you have a larger volume of semiconductor going from whatever this is like 70, 100 micron stripes up to 1,100 micron stripes. You have like 25% more emission area and you get 25% more power capability at the same time. So just as an example of how that's worked in the last few years, since 2007, the power per semiconductor bar has roughly doubled, with the FBH playing a significant role in getting there. For continuous wave, for pulsed bars, for particle accelerators, for example, with continuous wave coming a bit slower behind. And this is an example from a recent paper, well, 2022, not the 5-year-old paper. But the trick is this peak power has not been going up. If you take a single device without making them wider or playing other tricks, nobody in the world has been able to crack this limit of about 25-ish watts from a single laser. What's the problem there? I had a detailed review of this just last year now, early last year. What could be the background behind that? I mean, looking at the technology in the last 10 years, high-power diode lasers have got a lot better. I mean, if you look at, this is a curve of optical power versus current, also voltage and conversion efficiency. The conversion efficiency here is these curves. And you've gone from a typical 9XX device in 2009 was maybe 55% efficiency at operating power. And now it's significantly improved up into the sort of close to 70% operating in the 60 to 65 at operating. So there's much less heat being generated. Oops, excuse me. And that's basically because of significant changes in how the devices are made. You go from if you look at a cross-section through the laser here, this is your optical waveguide. This is where your electrons and holes combine. And this is the optical field held around them. You have a very thick P side waveguide. And this is where most of the optical loss and most of the optical absorption happens. In modern lasers, you use a very much more asymmetric structure with a clever refractive index profile that holds the light very well where the gain is, but removes the majority of this highly resistive and highly lossy p-doped material. In addition, you can put in sophisticated current blocking structures that stop carriers going where you don't want them to laterally in the structure. Huge improvements. These devices have a much better temperature sensitivity. The threshold current and the slope themselves both change much more slowly. The red is the new ones than reference devices. But that hasn't helped the peak power very much at all. So you have a much more higher performing device with most of the characteristics are better, but still the peak power is stubbornly not moving. And if you look at the temperature sensitivity of the characteristics of the temperature sensitivity of the laser, you would expect simple extrapolation, you should have doubled the power, and it's barely moved. So that's in terms of research, then what on earth is happening there? So you looked back in 2015, you put current into your semiconductor, you could lose it to the side. The current you put into your gain region could hop out and be lost again. It could go into the gain medium and be absorbed or not be coupled out correctly. Do they get to the quantum world? Do they even escape? And in the past 10, 15 years, we've done a lot of research to try and understand the problems. You can get rid of current spreading. You can stop carriers escaping. You can have a very good outcoupling with a low optical loss. So all of the photons get out and be used. So what's the problem? Why are you losing so many? One trick is to make a high power laser, they have to be very long, so the heat can come out very easily. Once you start doing that, you have a large variation in optical fields between the front and the back. This large variation in optical field leads immediately to a wide variation in carriers from front to back. There are a lot of carriers collecting at the back. In this picture, this is the back facet, this is the front. And this large collection at the back can lead to an awful lot of losses. And this is the calculation from, 10 years ago, but roughly 10 years ago from Hans Wenzel's team at the FBH. You see quite substantial power loss just because of this non-uniformity in the resonator, which you have to use to cool the devices well enough to run them at high powers. Other problems with that is if you have a high front to back temperature difference, then you have a much stronger thermal lens at the front. That means you squeeze the optical field closer and closer together into the middle of the device, even though you're putting current in everywhere, and this leads to these great big spikes developing. So you have high carriers at the back just because of the natural front to back photon density, high spikes at the sides, and once you start doing that, then you start losing lots of carriers, and your efficiency and power crashes. So in short, broad area lasers are large area devices operated at high currents and powers. You see very strong temperature non-uniformity, and this is predicted to trigger high losses, even when everything else is extremely well optimized. It's a kind of inherent characteristic of the resonator. So can you see this in experiment? If you make special lasers with a hole in the substrate, everywhere you have carriers, they emit some light in all directions, and the intensity of that light tells you how many carriers there are in short version. So if you image this into the camera, you can actually see the carrier profile within your resonator. And here in 10 amps, we were able to see very intense emission at the back and at the front edges. So it matched what you predicted in simulation. This is some nice case studies from the last couple of years together with the University of Glasgow. So you can quantify the impact by comparing pulsed and continuous wave measurements. You do a couple of different configurations where you have a high reflectivity output facet on the diode lasers. So this accumulation is a bit flatter, and you can see what that does. So if you have here, this is comparing pulsed measurements at low and high current for the two different coatings. So here, pulsed at low current, the temperature dependence is the same for everything. If you look at high current, when you have a large front to back difference, so a big difference in your photon field along the resonator, with the low reflectivity on the front facet, you see a very fast drop in the slope with temperature. So you have basically here, this is a temperature driven loss like leakage. Going from here down to this curve is a current driven loss. So bias dependent leakage, and this part is the longitudinal field driven loss, longitudinal spatial hole burning. So you can doing your best to quantify it experimentally. If you then compare this to how the slope varies just by running the device hotter in continuous wave mode, it's dramatically worse, meaning that raising the average temperature is much less damaging to your laser than raising the temperature differences inside the semiconductor that leads to local waveguiding and carrier losses. So what can you do? Again, you move to an ever more asymmetric structure and an ever higher gain to suppress the carriers in the quantum well. And slowly by doing this, we've been able to narrow the gap in slope as a function of temperature between continuous wave and pulsed. The other thing you can do is vary your current along the resonator by making a specially constructed device with many separate contacts along the chip and a special carrier, and varying the front to back currents. And in this way, you can reduce the amount of heat that goes to the front of the laser. By doing this, we've been able to reduce the heat. This is looking at the temperature along the resonator by following the local wavelength of the laser, which is a pretty good thermometer. You can flatten the temperature profile. You can reduce the amount of carriers at the front, and you can increase the power at the front. Here, for an example, with a 20% front facet. So it genuinely helps, but the benefit is smaller than we hoped for. It's like just like a 20% benefit. We thought we'd get as much as a doubling. We need to do more work there, and yeah, there's much more to do. We had a nice presentation at Photonics West earlier in the year showing progress. In fact, these segmented contacts with a lower current at the front than the back also strongly narrow the far field because you're reducing this additional thermal lens at the front of the resonator. So again, a lot of hard work to understand why power is being limited, why far field is being limited, and then address it by changing your structure. You can also look at what is limiting conversion efficiency. This is of extreme importance to people building large systems like EuPRAXIA, or to the fusion community, or guys making industrial machine tools where the cost of electricity is a huge part of the system cost. What can you do there? Again, you have a similar problem that you've had a peak conversion efficiency out of the semiconductor has been stuck worldwide at around about 70% for the last pretty much 10, 20 years. What research is focused on is pushing the operating efficiency to higher and higher powers. So the points you're using your laser, you can get the benefit of this peak efficiency in more and more applications. This is essentially done by reducing your electrical resistance and reducing your rollover, so the device stays in a nice straight line to higher and higher powers, and you don't consume more and more electrical energy by a resistance. And again, these very asymmetric vertical structures have helped to do that. This gap is getting smaller and it's pushing to higher powers. Also by using wider resonator devices, that also helps. So we've, roughly speaking, the optical loss and the electrical resistance in a standard diode laser is roughly halved in the past 10 years. So one big limit that's left is the slope, meaning a large part of that is losses of carriers. Okay, so limits to beam property. I mean, we'd love to talk about this, but I mean, there's a review we published about 5 years ago. Recommend you to go look at that. Much detail inside, or I can happily talk to people afterwards how we have been working on that. Also, though, it's an important thing for the users. How can you make the beam coming out of your diode lasers that you use to pump your system? How do you make that beam as small as possible so you can couple them more efficiently? Okay, so jump down to a little bit more detail on progress for diodes for fusion energy, which is a fairly attractive topic for us. Right, a very important topic for us right now. So why inertial confinement energy fusion? Why fusion in general? Stolen some slides from Professor Hefner from the Fraunhofer Society here. So as we look as a function of time, this is in Germany. As time progresses, there's going to be a larger and larger demand for electrical energy. This is the requirements, and this is the demand. And there's a real challenge to match it. You look like in the next 20 years in Germany, there's going to be roughly 2 to 3 times as much electrical energy needed. So you'd like to have carbon-free source with diverse fuels, environmentally sustainable, safe. You can have a very high base loads demand rather than this variability you get from solar or wind. So it's got it's very exciting, very important opportunity. This is again a slightly old slide. Livermore's done it many times since then, but there's been this ability to trigger in the lab megajoules of energy creation larger than the energy input. So it's a reproducible laboratory demonstration. I like to say it's equivalent to the first demonstration of the Ruby laser 50 odd years ago, where it's shown that it can be done. It can be done controllably multiple times and understandably in the laboratory. This is a green light for developing applications, bringing it actually into the field. So, but if you look at a snapshot of what's happening inside the diode lasers, again, nabbed a slide from one of our collaborators, from Ricardo Betti here. At the moment, it's done with a big range of capacitor banks, many flash lamps, a large solid state laser frequency conversion. You make a very sophisticated laser pulse, put it into extremely sophisticated targets, and then you use it to generate the fusion energy. And you can do just a few pulses per day. You need to do many times a second if you're going to make this as a real application ready unit. Industrial diode lasers give you a path to an economic solution. Germany's, of course, as the viewers know, very strong in this field. You can replace this whole section with economic QCW stacks of bars. Example here from Crump. Other guys like Leonardo, for example, do these also very well. You can build them into megawatt class pump arrays, form them into optics, deliver them to an amplifier crystal. For example, here shown the Happel system at Eli. It's a similar approach, but on a massively larger scale. Extremely good for what you'd call compared to fusion, a small system, but it's far, far too expensive at about, I don't know, €0.5 of a euro per watt to €1 per watt. And it's got to be probably something like 50 times reduced in cost to make an affordable power station. You can't afford to be spending €1 billion plus on your diode lasers and make money out of a power plant. Also, you'd need around 50 million bars for a single power station, so it's much bigger than the actual world production. Much to do. So then there's a big program at the moment. There's this nearly 2 billion being invested in Germany on the topic. We're happily part of this, as there's a BMFDR project Helios, which is specifically working on much higher power diode lasers and everything around them, being coordinated by Crump and the ILT with many leading lights of industry. How do diode lasers fit into the system? You take one of these nice diode lasers, a copy paste from earlier, you make lots and lots of them, put them into these laser drivers, and assemble them into a fusion power plant. Simple as that, right? Easy to say. This is sort of our part of the chain, basically. Again, to a little bit more detail on the requirements, you'd need around about 30 to 50 gigawatts per power plant. So, and you'd love it to have it at roughly a dollar cent per watt or euro cent per watt. But this is about 10 to 100 times larger than about 10 to 100 times larger capacity would be needed as this spread across the world and was used across every country. I mean, there was an estimate back from 24 that our colleagues and Coherent happily, in a friendly way, provided. You need a current laser facility could generate roughly 3 gigawatts per year. So, I mean, at the moment, they're delivering maybe 1.5 gigawatts for fiber laser power. And then if you were running that continuous way, it would be roughly twice that. Costs right now are something between maybe around half a dollar per watt. So that would be, you'd need to be getting around about 10 to 20 times lower. Right. So, but even if you manage to get this tenfold reduction in price and tenfold higher level per power, the diodes would still be, say, 30 to 50% of the entire facility costs, depending on how you cut it. And there was a nice paper from Livermore at Photonics West earlier in the year that sort of backed that up with a bit more detailed calculation. It's possibly the largest single cost element in the entire fusion facility. There are many other absolutely essential topics that need much investment and much engineering to make a plausible plant. But diodes are certainly a significant part of a very significant part and worthy topics of study. Again, this is a repeat, but we're working hard. We've been working hard to make power higher. There is industrialization happening now. Several companies have published either their intention or their ability to make 1,000-watt bars as a product, which is roughly a factor of 2 bigger than the industrial standard a couple of years ago. Also, another helpful topic would be putting wavelength stabilization into the semiconductor. So if you can bring a grating into the semiconductor, that could potentially remove one of the biggest yield hits, i.e. biggest cost driving elements in diode laser fabrication by getting rid of wavelength yield loss. There's a natural variation uniformity across semiconductor wafers that leads to a small drift in the lasing wavelength. And in practice, that's one of the biggest hits and can be one of the biggest cost hits. So if you can implement a grating in the semiconductor without excessive loss in performance or reliability, then it's quite an attractive way to move forward. So we've been working on this at the FBH for some years now. Here's a slightly older result. We were getting around 900 watts out of a 980 nanometer bar. We're working hard at other wavelengths. And of course, the other thing, you have the benefit you can pump narrow lines, so that has a potential of making your whole system more efficient. And may also simplify the design of your solid state laser as well, maybe. Like I say, every bar is always at the right pump wavelength, so you have the potential for large cost saving, and there's industrial prototyping happening right now. And we had a paper with Crump just last year showing some 885 nanometer grating stabilized lasers as an industrial prototype. Enlight in the States, my old colleagues there have a fiber laser pump that's available in volume now with integrated gratings in the semiconductor. We just had a nice result just earlier this year where we were able to show for the first time 1,000 watt per bar inside a narrow line at 885 nanometers, which is an important pump wavelength for fusion. And I'll show some more results, some more details on that next month in Kumamoto in Japan. Another idea, how can you take the power even further for even stronger power scaling? So here, for example, this is how a cross-section of a current semiconductor laser. We have a P and an N side. There's a PN junction with the quantum well in the middle for generating the gain, and then the light is held in the center. Why not put more of them on top of each other into one semiconductor? Wouldn't that be a good thing to make them possibly a little cheaper as one step grown integrated low-cost source? This has been proposed for decades, and it's now possible with very high performance due to strong technology progress in these tunnel junctions that link the semiconductor layers together, which are low resistance and low loss. When you start putting multi-junction in there, these are added these red points. It's been a hot topic in the diode laser research in the last couple of years. You're getting another factor of 2 in power in continuous wave devices, which would be consistent with powers into the multi-kilowatts per bar, which would be another cost reduction. This is for a couple of years ago from a group in Japan. I think it was, I hope I say this right, Dogain, I think that was right. Apologies if I misspeak, but it's been shown that you can do this in QCW mode, like with an appropriate pumping configuration, operating condition suitable for pumping a high energy solid state laser. So about up to 2 kilowatts at 1,000 amps has been shown. And you see there's a much steeper development in terms of power. So we're all very excited to push further in this direction. So it's actually, people are moving rather quickly to going from 500 from 2-3 years ago as standard to the first industrial offer of around about 1,800 watts per bar, which has the potential to make the semiconductor 4 times cheaper. There's a couple of nice papers in the last few years from Coherent. There's another one the Photonics was this year, I forgot to cite, but they are basically becoming commercially available. This further factor of 2. We have these decoupled, just one laser on top of the other. So what's the next step after that? So there's an approach that the Ferdinand-Braun has been following for a few years. If you look here, you have a single junction going to multi-junction. That looks rather nice, 3 times the power. The trick here is that these different layers, you can have quite a lot of difference in temperature between them. So each of these has a different wavelength. And when you have a very thick structure, again, you have this trouble with current spreading where you don't like it to, and that can also compromise your performance. This is wonderful technology, but it's not perfect. We have a different approach we're pursuing at the Institute to try and take this whole idea a bit further. We do a coupled multi-junction. We throw away these cladding layers in the middle, squash the entire structure together, and you actually have one coupled mode where the zeros are the location where the tunnel junctions are, so you don't get losses in them. You get 3 times the power, but it's in one mode, so you can potentially collimate it. You also have in the vertical structure, compared to this solution on the left, the multi-junction, you actually have maybe like you lose a lot of material. So the electrical resistance must also be smaller. So you have the potential for higher efficiency. And then the further benefit of this is because it's one mode running through all of the structure, you can put a grating into the device and stabilize the spectrum at the same time. So you can have this potential for this wonderful everything at once structure. All right, so it sounds great in terms of a few colored blocks on a PowerPoint slide. It looks very promising. To make it work is another task. Now the LiDAR team at the FBH has been working on these for some years now. We have been able to show in short pulse mode, just a few nanoseconds, that you can achieve 2,000 watts out of a single bar in a narrow spectrum with a triple grating. If you could combine this approach with a 1,000 watt bar approach or 1.5 to 2 kilowatt single junction approach, maybe you could get up to the 5,000 watts per bar, maybe. And that would immediately give you a 20-fold increase in, a 10-fold increase in power compared to what industry was just a couple of years ago. Maybe that could give you a route to getting all of the cost reduction you need for fusion by using just the right laser technology. So the latest data from the LiDAR team, not my work, but many smart scientists at the Institute made this happen, other people. It's got 420 watts out of a single 200 micron stripe. There's a peak power test with a multiple active region structure just last year. If this power was reproduced on a bar level at a centimeter, this would be 15,000 watts out of a single bar. Right. So, of course, LiDAR uses 10,000 times shorter pulses. There's no heat. This is a one-off demonstration. On the other side, there was a comment from Osram in Photonics West this year. They can also get similar powers from a single similar size stripe from the industrial chips with a multi-junction solution. So it's getting there. There's a plausible path. So if you're interested in learning a bit more, we put together a summary together with Lawrence Livermore just last year. There's a paper in Optics Express that's open access. You can read a bit more there. So if you look at this next point, so if you wanted to make an ultra low cost 870 nanometer multi-junction bar, there's a lot of things you need to do. The everything at once solution. You want to have wonderful process control for high yield, which means you've got to want to be able to control this grating at the back very carefully. You want to have precise control of this rather complicated, rather thick epitaxy. You'd like to have rapid early defect identification, automated processes, so you don't need 100 scientists be controlling and reviewing every step. With defect identification, for example, by implementing artificial intelligence techniques to make the defect identification fast and low cost. You'd like to have a device that's a facet technology that can survive the powers, that works well at 870 nanometers, where the vertical structure tends to have a high aluminium in it, which oxidizes like crazy. So you have to have a very robust seal of the facet. You'd like to have, with that technology, reliable 1.5 kilowatts per junction, say. So when you stack 2, 3, 4, 5 of them on top of each other, you can get up into this 5 kilowatt total chip. It's got to be suitable for making very high throughput manufacturing, compatible with these multi-junction designs, so that the facets need a lot of work. The process needs a lot of work. Of course, the vertical structure needs a lot of intense work to get the conversion efficiency up and to make it compatible with high power. Plus, you would need, again, device and technology for efficiency. It would need to go into a cooler that could handle the additional heat. You'd need to have appropriate current drivers that could give you the hundreds of microseconds of pulses in a small, compact, efficient unit. But if we could crack all of those topics that are within the realm of science and engineering, you could have a transformative effect on the fusion industry, if we can do it. So to reach a conclusion slide after many words and many topics. So we've been working to span with high-power diode laser research at the FBH goes from studies of limiting physics of the semiconductor through to emerging enabling application, from studying of photon and carrier loss mechanisms to efforts to engineer for more power, to looking at totally new device concepts such as the pixel, enabling new applications from additive manufacturing to pump direct diode to advanced pumps for fiber lasers, to close work with the EuPRAXIA community and the PACRA community to make better particle acceleration, diode lasers for particle acceleration, through to advanced work to also advanced work to move the inertial fusion energy field further. We've been able to show pretty strong progress in understanding the limits, but there's a definite key challenge due to non-uniform temperatures at high drive currents. That we need to work hard to scale conversion efficiency and beam quality, which could fill another hour's presentation. Pixels are extremely exciting, but there's an awful lot to do to enable their use in real industrial efficiency demanding applications. And of course, as I spent a lot of words talking about, much higher performant diode lasers are needed to enable inertial fusion energy. And we have a promising roadmap, a promising path to get there, but it's going to be a lot of work. We're going to need a lot of skilled cooperation partners, and progress across this whole area is going to help the whole field of high power lasers in general. And we're pleased and proud to be part of it, pleased and proud to be part of the EuPRAXIA community and the PACRI team, and to work hard to make many new and exciting laser applications possible. And much to do, future is bright. Thank you so much for your time. Again, apologies again for the slight delay at the start. Much thanks to our many cooperation partners. Trump has been a big and important partner for us, amongst other fine colleagues. Projects such as HotStack, funded by the Profi Channel, which is also supported by the European Union, the BMFDR, EuPRAXIA and PACRI projects, and of course the entire team of the Ferdinand-Braun, Photonics and Technology departments, the Prototype Engineering team, the Institute's leadership, Professor Shaler, Dr. Ironman, and the previous head of the Institute, Professor Trenkler, and of course to my colleagues and friends in Glasgow. So thank you very much. And with that, I will close the talk. Thank you. Ready for questions.
Thank you very much, Paul. That was a fantastic overview of everything there. So yeah, we do have the Q&A function that's still open. So if anyone does have any questions, please just drop them in there and we can put them to Paul. I do have a couple to begin with. You've covered quite a lot of examples there of how these diode lasers could be used, and I noticed that the bar system that you had, you even used the phrase copy paste a few times. Do you expect that to still be the case with this new idea, this everything at once idea, or do you see sacrifices in other areas, such as like the beam properties that are produced inside the profile might not be exactly what's needed in say, for example, like EuPRAXIA or EuPRAXIA Light Facilitator?
I mean, this is kind of the sketch of what would go into a fusion facility. I mean, in fusion, you need enormous numbers of lasers. Many millions of diode lasers go into one of these facilities. Excuse me, and a convenient way of collecting all of those lasers and cooling them is the bars and then putting them into stacks. So I think for the fusion application, and also certainly a very large and very technologically exciting and very important thing, such as the EuPRAXIA laser, will also need a large number of bars. It may not be millions and millions of bars, but certainly many thousands, many thousands of lasers. So a similar approach is followed. And if you use one of these multi-junction structures of any configuration, whether these fancy coupled multi-junction or a more conventional decoupled multi-junction, yes, your far field is a bit more complicated. The beam quality in the vertical direction out of the semiconductor is a bit more structured, and it is not, and nothing comes for free. I mean, if you look at how these things are used, you'd have like a slab of many stacks. This is like a box, sort of yay big, full of lots and lots of blocks of diode lasers. The beam that comes out of that box goes through normally, or can, in some configurations, be put through a homogenizing element or delivery system that in principle can compensate for there's a more structured field. Yeah, so it is possible. We had in our Photonics West talk, we did a very quick initial ray tracing estimation on how you could cope with a more structured beam out of a stack using one of these multi-junction solutions, and it looked like it wasn't that bad. Like essentially that a relatively straightforward homogenization system of a couple of crossed arrays of microlenses could completely compensate the additional beam non-uniformity from a multi-junction stack. That was a quick test. What a real system would look like needs some careful analysis, and that takes some time. On the other side, if you're offering more power for less money, normally we can find a solution to getting that into people's hands. I mean, I'd take as an example, when I started my career in semiconductor lasers, I was working on communication devices. And when you do zeros and ones data coming out of a laser, we were under extreme pressure to have the cleanest eye diagram, the most perfect on-off profile of zeros and ones out of your semiconductor possible. Now, in a modern communication system, the eye diagrams, the zeros and ones, are much uglier because you put many layers of data on top of each other into one signal. So you've accepted like a 4, 5, 10-fold more data transmission at the cost of having to be more sophisticated in handling a less clean eye diagram. In the same way here, the path to maybe getting as much as 5 to 10 times more power per semiconductor laser bar than is currently possible, at the cost of having to handle a more complicated beam. Many people will take that choice. If you can't, then of course you have to find another way forward.
Thank you. So we have another question here. So, what are the challenges to scaling up industrial production levels of diodes for a fusion plant?
Long and demanding. There was a very nice presentation by Stuart McDougall from Crump in Photonics West earlier this year, that came out of some work within the Starfire Corporation, or coordinated by Livermore, where they looked very specifically at how you could move the costs down based on real prices of industrial machine tools, sensible, conservative estimates on labor costs, on gold costs, on gallium and arsenide costs, and they showed a path of how production scaling could bring your cost down. These are not remotely trivial tasks, but practice tasks. For example, from the developing the LED industry, they've also had to go down a similar path up to similar volumes to what fusion might need. So it's to get their production scaling by careful, by doing well-designed facilities. But part of the path to get there was also very clearly, explicitly power scaling of the semiconductor. So you have known but challenging and very expensive production scaling, which you need a sufficient demand in your hands to justify that cost, or very patient and very rich investors. And you need new technology with higher powers that is properly and carefully demonstrated, reliability tested, and quality controlled and qualified for use in a large system with low failure rates. So those are two clear things. That the production scaling is facility cost and investment, and then there's technology cost and investment to make the semiconductors ready. So with Stuart's presentation, they were estimating they could get down to, I think, 2 to 3 or 4, something on the 2 to 3 cents per watt if you could bring a 1.8 kilowatt bar into production at no additional challenges compared to what we have now with making semiconductors. You'd like to have another factor of 2 or 3 to get it down to the cent per watt, which is the ultimate aim of the effort, which our 5 kilowatt bar approach would eventually help, hopefully eventually deliver.
Great, thank you. Probably final question in terms of the time we have now. What is the expected lifetime of diodes for fusion? How often would they need to be replaced?
I mean, if you're building the diode fusion power plants that's using extremely large numbers of devices, the failure rate would need to be very low. You don't want to be pulling devices out every few days. You want to plug it in and leave it alone. The failure rate is going to have to be tiny. The current phase, where you'd like to have possibly be building beamline demonstrators to test your components, to demonstrate different parts of your system can work. That's a much smaller, maybe it's a 100th or 200th of a full laser system, and then it may only need to work for a few years to do sufficient demonstration. That's a bit more short-term sensible goal. And there we had an estimate of Photonics West. I mean, the paper is on our website. There's an open access version of it. The author's copy, just go click on it and it walks you through the analysis. I mean, if you take some typical device reliability numbers from the literature and make a first just sort of sensible estimate, you'd have, like, if it was a diode laser single emitter with they call it a 500 fit level, which you have oh gosh, was it one failure per 500 million hours? I think that's right. I'm going to say that wrong now and get myself into trouble. But it's like an industrial number, standard industrial number. With that as a benchmark, you would have a single stack would have a lifetime of 10 to 20 years, but you'd end up with maybe about 4 to 5% average failure in a beamline, which is built of an assembly of, say, 1,000 to 2,000 stacks. So you'd have you could plug it in, let it run for 2-3 years, do all your experiments, and then you'd have maybe 10-15% of your stacks would be gone, and the rest of them would still be within their operating lifetime, and everyone would be happy. And that kind of level would be a life test to demonstrate that, a qualification to demonstrate that is plausible within like about a year's effort. So if you had a technology now you liked, maybe with the year's well done, carefully organized qualification, maybe you could say, yep, that technology is usable, let's go build a beamline with it, and you move forward. A full system qualification is a much thornier topic, and that again could take a half hour to an hour's presentation to walk through what that would mean.
Brilliant. Okay, well, I think we'll call it a day there. Thank you very much, Paul. Like I said, that was an excellent presentation. The video for this will be available on YouTube, so please take a look at that afterwards. And then if you do have any follow-up questions for Paul, you can reach him on LinkedIn, I suppose, we're best place. Yeah.
Yeah.
Yeah. Brilliant. Okay.
Okay.
Well, thank you, everyone. Thank you for joining, and we'll see you in the next seminar.
Thank you. Take care. Thanks again, Joe, to everyone for the opportunity.